Welcome to The Explainer. Today, we're looking at an absolute collision between two of the most fascinating fields in modern science, artificial intelligence and quantum computing. For millions of us, chatbots powered by large language models are just a totally normal part of everyday life now, right? We use them to write emails, brainstorm ideas, summarize huge documents. But behind the scenes, there's this urgent, massive hardware crisis quietly threatening the entire future of artificial intelligence. These AI systems are growing at lightning speed, and scaling them up is becoming an incredibly costly, resource-intensive nightmare. So today, we're going to explore a groundbreaking new approach that might just save AI from its own explosive growth.
Okay, let's dive into this staggering number. 2 to 5 trillion. That is the estimated number of parameters in the upcoming GPT 5.5 model. Just take a second to really wrap your head around that scale. 2 to 5 trillion. It's almost unfathomable. When we talk about AI getting smarter or better, what we're really talking about is this explosive growth in numbers. But this scale, it's actually showcasing the sheer absurdity of AI's current trajectory. We've literally reached a point where simply making the numbers bigger is triggering a massive physical bottleneck.
Section 1. The AI memory problem. It's so easy to think of artificial intelligence as just invisible code floating around in the cloud somewhere. But this massive scale is actually becoming a literal, heavy physical burden for tech companies.
To really understand why this is such a physical burden, we have to look at what a parameter actually is. Basically, parameters are the adjustable settings in a large language model that determine exactly how it processes and generates text. You can think of them like, billions or trillions of tiny little volume dials and switches. The model learns how to turn these dials perfectly during its training phase. But here is the stark reality of the situation. Every single one of those trillions of settings takes up actual, physical space on a computer chip. They require massive memory banks inside giant data centers, and they are constantly drawing power.
So the crucial point here is this giant catch-22 of modern AI development. More parameters generally equal better performance. If we want chatbots like ChatGPT or Claude to be smarter, more accurate, and more helpful, we absolutely have to scale them up. But because of those physical constraints we just talked about, the resulting memory demands are becoming impossibly expensive and just really difficult to manage. We simply cannot keep building bigger and bigger data centers forever. We need a completely different approach.
Section 2. The quantum circuit solution. It's time to start working smarter. Borja Espurua and his incredible research team at Multiverse Computing over in San Sebastian, Spain, realized we can't just keep throwing more classical hardware at the problem.
According to their recent preprint published on the archive server, they developed a truly elegant alternative. Instead of adding vast numbers of new, memory-hogging classical parameters, they proposed something totally different. Inserting small, specialized quantum circuit blocks directly into the inner workings of an already pre-trained large language model. It's kind of like taking a standard car engine and swapping out just a few key components with hyper-advanced futuristic parts.
And this brilliantly illustrates exactly why their approach is so powerful. Traditional classical parameters require a massive physical footprint to scale up, but these new quantum blocks, they can encode incredibly complex mathematical relationships in a highly compact form. Because of the totally unique laws of quantum mechanics, they achieve in a tiny footprint what would otherwise require huge, sprawling amounts of conventional memory. It's like the ultimate compression tool. So how does this actually build into a working architecture? This is vital to understand. They aren't suggesting we throw away our current computers entirely. Instead, they're creating a highly efficient hybrid system. The original, pre-trained large language model still runs on a standard computer. But when it hits those really complex calculations, it essentially tags in an IBM 156-qubit superconducting quantum processor, which then executes those incredibly dense, compact quantum components. It's the perfect division of labor, letting each machine do exactly what it does best.
Section 3. Testing the hybrid system. So, they had the theory, but what happened when they actually tested it on Meta's Llama model? Let's take a look.
They ran their test on Meta's Llama 3.1 8B, which, as the name implies, is a model with 8 billion parameters. Now, to enhance it, the team added just 6,000 extra parameters using their quantum circuits. Think about that crazy contrast for a second. 6,000 parameters added to an 8 billion parameter model. For context, that represents an increase of less than 1/10,000% to the model's overall size. It is practically microscopic.
And the outcome of that tiny microscopic addition was honestly astonishing.
Despite only adding those 6,000 parameters, they achieved a measurable 1.4% reduction in perplexity. Now, if you aren't familiar with perplexity, it's essentially a key metric for how confused a model is. So a reduction means the model is reliably predicting the next word in a sequence much, much better. This is a massive David versus Goliath scenario, right? That incredibly tiny addition of quantum parameters actively improved a heavy-hitting 8 billion parameter model.
To really prove the science behind this, the team also ran a systematic study on a smaller model called Small LM2, which has about 135 million parameters. Using this smaller size made it way easier to track exactly what the quantum circuits were actually doing, and the results were incredibly consistent. First off, as they increased the size of the quantum components, the model's performance steadily improved. But here is the real game changer. The quantum-enhanced model was actually able to correctly answer specific questions that two purely classical versions of that exact same model got entirely wrong. It didn't just save space. It unlocked totally new capabilities that classical computing just couldn't reach on its own.
Section 4, the future of AI. Now, we do need to ground our excitement just a little bit here. Right now, these early performance gains are pretty modest, mostly because the quantum hardware itself is still in its infancy. But honestly, that is exactly why this is so exciting.
The researchers noted a really powerful takeaway in their paper, stating they are, quote, opening a fundamentally new path for developing more capable AI without the runaway infrastructure costs that threaten to define the field's future. Getting this to work on real, widely used models is just a massive first step. As IBM and other tech giants build quantum processors that are stronger, more reliable, and just all around more powerful, the improvements we see in these AI models are going to scale right alongside them effortlessly.
Which leaves us with this really provocative question to ponder. Will quantum blocks save AI from its own runaway growth? We are rapidly approaching the physical limits of our digital world, where we literally just can't build data centers big enough to house the next generation of classical AI. But by looking to the fascinating quantum horizon ahead of us, we might just have found the ultra-compact key to unlocking the true potential of artificial intelligence. Thank you so much for joining me for this explainer. Keep asking those big questions, and I'll catch you next time.